Electrolysis. Galvanic cell and electrolytic cell. What's the difference? The top one, galvanic cell, this chemical reaction occurs spontaneously and it to drive the electron flow. What do I mean by that? The reason the electron flowing is because of the anode, a more reactive metal, flow to cathode, the least reactive metal. So which, because of the difference, it drives the electron flow. Electrolytic cell different. They're using electricity to drive the electron flow. So they're using the power source from outside power to drive the electron flow. What happened without the outside power? Without the outside supply, the reaction will not happen. So, once you take out the battery, the reaction will stop. So, the reaction is non-spontaneous. If you study the anode, cathode, and electron flow relationship, they will be very identical. Anode always oxidize. Electron flow always from anode to cathode. Cathode always the reduction. And then what is the difference? The difference is the sign different. Anode in galvanic cell always negative, but in electrolytic cell, anode is positive. So the other will follow. Cathode at galvanic cell become positive, electrolytic cell become negative. So keep in mind, anode in galvanic cell negative, but on electrolytic cell, anode is positive. Now look onto the standard reduction potential difference. As normal, anode reverse arrow flow down to cathode, same arrow. Anode reverse arrow flow down to cathode, which is same arrow. Keep in mind, anode always reverse arrow, cathode always same arrow. And this reaction we know is flowing down. It happens spontaneously. In standard reduction potential for electrolytic cell, anode still reverse arrow, cathode still same arrow, but the flow different. Anode flowing up to cathode, anode flowing up to cathode, and this does not happen spontaneously. You need to have the outside power to drive it up. So on summary, galvanic cell, anode flow down to cathode. Electrolytic cell, anode flow up to cathode. Now keep this in mind. Now let's start. Now let's look onto the electrolysis of the molten salt. Molten salt, in molten salt, also, if you put molten salt into the anode and cathode, first, anode is the positive rod we just been mentioned. So if you put this molten salt into this solution, what will happen? the negative ion will flow towards the positive rod. The positive ion will flow through the negative rod. So, chloride, negative ion, will flow towards the positive. Sodium, positive, will flow towards the negative cathode. Now, we look onto the standard reduction potential. Cl and Na, we highlighted. So these two is the one reaction. And how's the electron flow? Remember, electrolytic cell from anode flow up to cathode. Anode is the chlorine ion become chlorine gas. So cathode is the sodium ion become sodium, so a metal. Now, once we highlight anode, always reverse arrow as our old rule. So, on oxidation, you write down chloride become chlorine gas. Cathode reduction, same arrow. So, reduction, sodium ion become pure sodium, gaining electron. And this is the way you write the molten salt by electrolysis. Electrolysis of aqueous solution. NaCl in aqueous solution, and that is a competition between ion. What's meant by competition between ion? Now let's give you an example. Earlier we learned the negative ion go towards the positive rod, positive ion go towards the negative rod. When there is two negative, both want to go to the positive rod, and both positive ion want to go to the negative rod, that is a competition between ion. And this happen in this case is a NaCl in aqueous solution. And what would it look like? The top, you will have the NaCl in water. Students were wondering, Cl minus Na positive, how come water right into negative and positive? What's going on? Look at water. Water is a polar molecule. You have the negative pole and the positive pole. So, in water, the negative side, like the O of the water, go towards the anode. And for the water of the H+, those positive side will go towards the negative cathode. That's why I say water, you can treat it like an ion. So now that is two competition. Cl and the negative of the water both want to go anode. Na positive and the positive part of the water both want to go to cathode. Now we look onto the standard reduction potential. Remember, anode flow up to cathode. Anode, what did you get on anode? You see water and chlorine gas on the table, and chloride. Cathode, you get sodium and water as a cathode. So I highlight 4 lines. Now Remember the rule, anode flow up to cathode. Anode, the arrow always reverse arrow as the rule. And so, cathode, always the same arrow. So now with these two arrows, now we look onto the potential value. Remember, reverse arrow, reverse the sign. So anode, reverse arrow, so the sign need to reverse. So chloride become negative. Water also become negative value now. And now look onto the cathode. How did you allocate the value? Same arrow, same sign. You don't need to change. So now, by this, we establish this value. Now, here comes an important rule. On each side, the most positive value is likely to be the winner, is likely to occur. So, you look onto anode. Look on anode. Which one's going to have the most positive value? Look onto anode. The most positive value, chloride or water? The most positive value will be water. So water going to be the one that react. Now look onto cathode. Which one gives you the most positive value? Sodium or water give you the most positive value? Also, water give you the most positive value. So in competition situation between ion, whichever, no matter anode, the most positive value going to react. Cathode, the most positive value going to be react. So from the table, you know the oxidation, anode oxidize. It is a water become oxygen gas and hydrogen ion remain in solution. Then how about cathode? Cathode is reduced. Water become hydrogen gas and hydroxide ion remain in solution. And that's the way you deal with this competition between ion. Now let's look on another example. Iron chloride in aqueous solution. And this is another competition between ion. As you see, two negative, both want to go to anode. Two positive ion, both want to go to cathode, the negative rod. Now let's look onto the ion. Here you have the iron and chloride and water, and they both in competition. And now let's highlight the standard reduction potential. Now we highlight the value. On the top, cathode, water and iron, water and iron. At the bottom, anode, water and chloride. Now we allocate anode oxidation, reverse arrow, cathode reduction, same arrow. And now we base on this reverse arrow, you will reverse the value. So now the reverse value you will allocate as here. Reverse arrow, and you will have the reverse value. Same arrow, you have the same value. And now you ask which one's more positive on anode? Which one's more positive at cathode? And here you can see the winner going to be water in anode and iron as cathode. So now you can write down the equation as below. Anode, water. Reduction cathode, iron. Now we look on factor. This will also affect electrolysis. Here we consider the concentration of the electrolyte. In aqueous solution, as in NaCl solution, it affected by the concentration. When the factor you're in a dilute NaCl solution, the result will be water react on anode and water react in cathode. When you're on a concentrate NaCl solution, the result could be different. So now let's look onto the table again. On anode, when dilute solution in dilute NaCl, the reaction going to be anode will be water, and because the most positive wind rule. Cathode also water, also based on the most positive wind rule. So on the table, I mark down water anode, dilute, going to react. Cathode, dilute, water going to react. Now let's look. How about concentrate? In concentrate situation, anode will be different. Anode this time in a concentrate situation, chloride will win. That is unusual. But you say, hey, the value is not as positive. How come chloride win? Now look onto the standard reduction potential table. Look at the value of water and chloride. They are very close, one next to each other. And being so close, if you have high concentrate of chloride, can make chloride win. So in a concentrate situation, the winner going to be chloride at anode. Cathode, still water win. Then would it be sodium win? Can sodium be the winner? No, why not? Look at sodium on the table. That is too much energy required. So sodium compared to water, the difference too much. So no matter what, you concentrate or dilute, always going to be the water win, and the water going to be the ones that you react. Now we learn the summary. Today we learn 3 parts. All is the anode electron flow up to cathode, which require energy. The first one, molten salt, molten NaCl, chloride as an anode, sodium as a cathode. The middle, NaCl in aqueous solution. So you have water and chloride at anode, and sodium and water as a cathode. Now, when we consider dilute NaCl and concentrate NaCl, we further highlight in dilute situation of anode, water react. In concentrate situation of anode, chloride react. And now look onto the top of cathode. Water always react in both concentrate and dilute. Sodium never react because it requires too much energy. Student, you require to know these three charts so that you can continue with your NaOH topic. So please understand this chart well so that we can proceed to our next topic.